Today our speaker is Henri Guenancia. He is now chercheur de recherche at Institut de Mathématiques de Toulouse, and today he's going to talk about variation of Kähler-Einstein metrics. Henri, it's our turn.
Okay, thanks for the introduction. Thank you very much for the invitation. It is my pleasure to be talking in this virtual complex geometry seminar today. So as Ming Chen was saying, I will be talking about the variation in different senses of Kähler-Einstein metrics, and this relies on two recent and less recent works with Junyan and Mihai Paun. All right, so I've divided the talk in three parts, but really mainly two. So in the first part, it's essentially this slide, and I want to give you the tiniest bit of background. I'm sure all of you are very much aware of this result of Aubin, Yao, and Yao, which somehow opened up many new doors and horizons in complex geometry. And it's the following theorem. So if you have a compact Kähler manifold that I denoted by X, and you fix a Kähler form theta, then under two very interesting geometric settings, you are able to get unique Kähler-Einstein metrics. So the first setting is if you work with a manifold that has ample canonical bundle, or equivalently manifold where the canonical bundle is positive, meaning that it admits an emission metric with positive curvature form. In that setting, then Aubin-Yao theorem says that there exists a unique Kähler metric omega that satisfies the Einstein equation Ritchie equals -1. It's associated with Kähler forms. Ritchie omega, the form associated to the Ritchie curvature is proportional with negative constant to omega. The second case that somehow has even deeper applications and like really change the landscape of complex geometry is Yao's theorem in the case where the first Chern class of X, or first Chern class of Kx, it's the same thing, vanishes as a real Chern class. And in that case, there exists a unique Kähler metric belonging to the fixed Kähler class, theta, such that Ritchie omega vanishes. Okay, so those two objects, negatively curved Kähler-Einstein metric and Ricci-flat Kähler metric, will be somehow central in my talk, and my talk will be divided in two parts from now on. First part being focused on negative curvature metrics, Kähler-Einstein metrics, and the second one on Ricci-flat metrics, and in a context where we vary the complex structure. Okay, so families of such metrics. Okay, so after this very brief introduction, let me move on to the first part, so negatively curved metrics, and more precisely family of those. Okay, so the general situation is the one of a submersion P from X to Y between two Kähler manifolds. And I assume that the submersion is proper and homomorphic. So each fiber that I wrote X sub Y is a compact Kähler manifold inside X. And now, so what is the relative Kähler-Einstein metric? So I assume that each fiber satisfies the property from the slide before. I'm going to switch. Right, this first slide, this first item here, if Kx is positive, then there exists a unique Kähler-Einstein metric with negative curvature. Okay, so I assume this for each fiber. Okay, so the canonical bundle of each fiber X sub Y is positive. In that case, so each each fiber x sub y admits Kähler-Einstein metric omega y. And what I'm saying is that there exists a canonical way, somehow better way than all the possible ways to do so, to find a 1-1 form that is globally defined on the total space X, and that restricts to the Kähler-Einstein metric omega y for each value y. So there, in general, there's no such object, right? If you just give yourself a relative 1-1 form, then there are infinitely many choices of global 1-1 forms that will restrict to the forms you started from. So here the reason, okay, I don't want to spend too much time on that. It's not that important, but if you're curious, the reason why we can do that is because there's a way to solve the Monge-Ampère equation that somehow gives the Kähler-Einstein metric in a natural way, in a way that takes into account the geometry of the total space. Okay, so this is the equation that I wrote down. It involves essentially choosing, once we have a relative Kähler form, all the other choices are natural and canonical. Okay, so that the details that are here are not so important. The important thing is there exists a canonical object, which is a closed 1-1 form, and that lives on the total space X, and that restricts to the Kähler-Einstein metric on each fiber. Okay, so it is strictly positive in each fiber, but a priori, there's no reason why it should pick up any additional positivity in the base direction, in the direction of Y. So this is where Schumacher's theorem comes in and tells us, actually, it is semi-positive everywhere, and even better than that, we know exactly in which directions there is strict positivity or not. Okay, so let me recall the setting again. I started from a proper submersion with a relatively ample canonical bundle, in compact Kähler manifolds. And I have this relative Kähler-Einstein metric omega, which belongs in the first class to the first chosen class of the relative canonical bundle, and it is semi-positive. So it's clear that it is strictly positive in the direction of fibers, but the theorem tells me that also in the base direction, I have semi-positivity. And the second part of the statement, which is very interesting, is that if you fix a fiber x sub y, then omega is positive near the whole fiber, if and only if the Kähler-Spencer map evaluated at y is an injection. 2 remarks before I move on to a brief idea of the proof. The first remark is that the theorem, at least the first part of it, the semi-positivity of the relative Kähler-Einstein metric, was proved roughly around the same time, maybe give or take a year or two, by Tsuji, and relying on completely different methods, and more specifically relying on prepotential methods, and so Benson's Paun variation of Berman. I'll get back to that later because this will play an important role in what follows. The second remark is that theorem has had a few generalizations in various twisted cases. I mentioned those 3 works by Paun in 2012, myself 4 years later, and Junyan, Mihai, and myself a year later, again in slightly different contexts. So if you're interested, you can have a look at the papers, but I won't be talking too much about that today. Okay, idea of the proof. How does it work? It's a really nice and neat proof, and that has the advantage to be somehow the strategy is simple enough to explain it in a slide. I think the idea is nice yet simple. And the key player in the proof, okay, so here I've assumed that the base is a disk, it doesn't change much. The key player is that V that I define with this formula here. So that V, what is it exactly? It's a vector field that lives on the total space X, okay? And it's something that has been considered by Hsu in his work on the Peterson metric in the 90s, I believe. And that vector V is, so here I gave you the local expression on X, but it glues to a global vector field, and it is defined by the property that it somehow it lifts d by dt, the vector field on the base, on the disk, complex disk. And it is essentially, it is defined using that relative metric omega. So there are several properties that V shares. I'm not going to mention all of them, but what's interesting for us is that somehow V will appear. Okay, let me just read the next definition. So I want to define the function C, which is a function on the total space X. And that's defined as the ratio of omega to the n plus 1 by omega n wedge dt wedge dt bar. And this is uniquely defined because omega is relatively Kähler. So omega n wedge dt bar is a positive form. And so if I divide omega n plus 1 by that quantity, I always get a well-defined number. It might be negative, it might be 0, it might be positive. At this point, this is just a smooth function on the total space. That's called the geodesic curvature of omega. And the key point is that equation, okay, that second order elliptic equation, geometric equation. If you fix a fiber xt, then the geodesic curvature C satisfies a very simple, very concise PDE, which is that minus the Laplacian with respect to that metric omega t plus the identity applied to that geodesic curvature C is nothing but the square norm with respect to omega of d bar V. Okay, so V is a vector field, and I take its d bar, I get a one form value in vector fields, and I use omega to measure all that, omega t. Okay, and in particular, this is non-negative. This is what matters, and generalized maximum principle. So first of all, even forget about the braces at the bottom of the slide. That implies immediately that C is non-negative. Okay, just by the maximum principle, because at the point where C attains its minimum, minus, so its Laplacian is non-negative. So minus its Laplacian is non-positive. And so this tells you that C is at least at this point equal to the normal, square normal of d bar V. So at its minimum, C is non-negative. In particular, C is non-negative everywhere. Okay, so this is how you get the semi-positivity of omega, because C is essentially the eigenvalue of omega in the base direction. Okay, maybe I shouldn't have said that. So this is the missing direction that we want to understand. C gives us the value, the eigenvalue in that direction. Okay, so we get that it's semi-positive, but actually we get better, because if you refine a little bit that maximum principle, it tells you that the infimum of C is dominated from above by a constant multiple, positive multiple that depends on some geometric data that I don't want to precise, times the L2 norm of d bar V. And why is this great? Well, because if the metric is not semi-positive, is not positive somewhere on the fiber xt, it means that C reaches the value 0, and particularly the L2 norm of d bar V is 0, meaning that d bar V is 0, okay? And d bar V is actually a representative of the image of Kähler-Spencer on that fiber of d over dt, and so that tells you that Kähler-Spencer is not harmonic, is not injective. Okay, so that concludes the idea of the proof, okay? And as you see, most of the work relies in establishing that PD. That takes some heavy computation. Okay, so let me move on to a context that's slightly different, which is manifolds of general type. Manifold of general type is just a projective manifold with big canonical bundle. Okay, and so there's a theorem that dates back to slightly after the EGZ times, so around 2010, something like that, where it was proved. So various statements were proved by different authors, and I just want to give the optimal statement here, and feel free to dig and see exactly who did what. The statement is the following. So we want to generalize a Yao's theorem, Aubin-Yao's theorem, okay? Because if Kx is ample, then in particular it's big. So we're trying to generalize Aubin-Yao theorem and construct a canonical metric in that setting. And the theorem tells me what? It tells me that there exists a unique closed positive one-on current in the cohomology class of Kx that satisfies three conditions. The first one is on a Zariski open set, non-empty Zariski open set of X, I get a smooth Kähler form. Okay, and that Zariski open set is given by the geometry of X, and more precisely, you take X and you remove the augmented base locus of Kx. And in particular, you remove all the base points of multiples of Kx, but not just that. You remove more points. You remove all the points where the eta fibration associated with Kx is not an isomorphism locally. So, okay, that's the first part. You get a smooth Kähler form on that big Zariski open set. That's Ritchie, that has constant negative Ritchie. Okay, so you get a Kähler-Einstein metric on the ample locus of Kx. So those are local conditions. Okay, you get a global current that satisfies these two local conditions. And the third one is a global condition. It tells me that omega somehow has what is called minimal singularities in the cohomology class of Kx. I won't say too much about it, but it essentially tells me that the potentials of omega with respect to a given representative, smooth representative, are as good as they can be. Two remarks briefly. So as of today, 2020, there is no proof of this whole theorem, okay, so 1, 2, 3 together, that does not rely on BCHN. Okay, and that's because from an analytic perspective, regularity in general big cohomology classes is a major challenge and major conjecture. Using BCHN, though, we can reduce Kx big to Kx nef and big somehow, and that makes the whole difference. Second remark, yeah. So I essentially emphasize an example of what I mean by minimal singularities. If instead of Kx big, you have Kx semi-ample, then condition number 3 just means that you put local potentials are bounded. Okay, so again, as good as they can be from the potential point of view. Okay, so now I'm going to do the same thing as I did. I'm going to look at these objects in family, right? The same thing I did with the usual negatively curved Kähler-Einstein matrix or canonically polarized manifold. I'm going to do the same thing for manifolds of general type. Okay, so same setting. This time slightly more different. I don't necessarily want to assume that all of my fibers are smooth. Okay, so I started from a projective fibration between Kähler manifolds, and I assume that each fiber, each smooth fiber, let's say, has general type. Okay, but I allow some fibers to be singular. And in order to state the theorem, I need to single out the locus where P is smooth, and I assume locus is the inverse image of a gyroscope instead of Y by P. Okay, so X naught to Y naught is a smooth submersion, proper submersion. And I can do the same thing as I did earlier with that relative Kähler-Einstein metric. I glue all of the, so this time singular Kähler-Einstein metrics that are defined on X sub Y for general Y. And I can glue them to a global 1-1 current that will live on the smooth locus of Px naught. Okay, by solving the same type of equation. There's a canonical guy there that somehow patches up all of my fiberwise Kähler-Einstein metrics, singular metrics. And the theorem that I want to explain is somehow a partial analog of Schumacher's and Tsuji theorem, that current omega that is so defined is actually semi-positive globally on X naught. And also, even if it only defined on X naught, it actually extends canonically to a positive current in the first string class of the relative canonical bundle. Okay, 2 remarks again. So this is somehow the user-friendly formulation of the theorem. We did prove something that is a bit more general in the sense that we allow to consider not just singular K metrics solving Ritchie equals -1, but we also consider twisted Kähler-Einstein metrics solving an equation that looks like Ritchie omega equals minus omega plus the curvature of a semi-positive line bundle with possibly single emission metric, and the condition that we require is that that single metric has 0 to low numbers. I'm not gonna say too much about that generalization, but it turns out that allowing Q line bundles is crucial, and that's also what makes the proof much more technical. But again, I'm not gonna get into the details for that. Second observation, it's actually really an interesting remark that if you combine that semi-positivity of the relative Kähler-Einstein metric in that case with recent estimates, potential estimates for singular Kähler-Einstein metrics, you can actually prove that the current omega defined on X naught has minimal singularities, not just fiber-wise, but globally on X naught. Okay, and that's not completely obvious. In particular, it tells, so that's it. Let me say, let's see. Let me say a few words about the proof. So full disclaimer, I hope you won't be too disappointed, but I'm not gonna really discuss the proof because it is extremely technical. There are lots of steps and lots of very subtle regularization procedures. And I think it is kind of mission impossible to explain even with a blackboard. So on this slide, I think it's just not reasonable to do so. I'll just give you the rough, nice idea that makes it work. And if you're interested in details, we can either discuss it later or feel free to look at the paper. Anyway, so I was talking earlier about Tsuji's proof in the ample case. That was completely different than Schumacher's. And we actually followed Tsuji's strategy because Schumacher's strategy would completely fail in the situation where we work with general type manifolds rather than canonically polarized ones. So the idea is somehow an idea that had come up repeatedly in complex geometry, especially since the works of Hsu in his proof of invariance of pure genera. That is a way to construct nice metrics on the canonical bundle by iterative processes. So here, in this very specific setting, the observation of Tsuji, the theorem of Tsuji, is that you can recover the Kähler-Einstein metric, which is a very transcendental object, as an iteration of purely algebraic objects. Okay, and those objects are Berman kernels. And the way you set up the iteration is really very natural. So you start from let's say that kx has sections. Okay, 1 times kx, let's say it has sections. So it means that you can form a canonical metric that is semi-positive, that has a positive curvature using the basis of the sections of kx. Okay, so that's for m equals 1. And then you want to construct a metric on m equals 2, so on mkx. And for that, you write 2kx equals kx plus kx. And you consider the Berman kernel of the adjoint bundle kx plus kx, where you endow the second kx with the previous metric that you had on kx. And then you consider an orthonormal basis for the L2 norm of the vector space of global sections of 2kx with respect to this L2 product. And that gives you another semi-positively curved metric on 2 times kx. And you iterate this for 3kx and so on and so forth. And that way you get a sequence of positively curved metrics on m times kx. And Tsuji's theorem is that when you normalize them properly, they converge to the Kähler-Einstein metric, or to the weight of the Kähler-Einstein metric. That is quite striking. And fundamentally, I think Berndsen wrote some years later a more concise and somehow, let's say, illuminating proof of that theorem that shows that really what it relies on is the Bergman kernel expansion, at least the first term, first 2 terms maybe. Okay, so let's say we know how to do this. Now we do this for every fiber x sub y. And the key point is if you consider relative Bergman kernels, and you can glue them, gives you precisely the relative Bergman kernels. And Berndsen's and Paun's theorem is that in that setting, if you have Bergman kernels of the form kx plus L and L is semi-positive, then the Bergman kernel on the total space has PSH variation, positive curvature. So this tells you that if you start from a family of manifolds with canonically polarized, which are canonically polarized, and you do for each of those manifolds the Bergman kernel iteration that I described in the first item, and you do that relatively, then for any m, you get a semi-positive metric on the relative canonical bundle, m times that will converge once properly normalized to the relative Kähler-Einstein metric. And because semi-positivity is preserved by passing to the limit, this is how you get the semi-positivity of the relative Kähler-Einstein metric. And of course, you lose everything concerning strict positivity versus semi-positivity. So that's in the ample case. And I will just tell you that in the big case, You want to run the same strategy, and in the end, it will be successful. But because at several points in the argument, the results are very much global, the fact that we lack understanding of a singular Kähler-Einstein metric near the augmented base locus makes the estimates much harder to get. And so this is why we need to use a lot of regularization procedures, but these procedures tend to kill a little bit of positivity, and this is actually a really serious problem to overcome. Okay, so that's it for now. That's all for part one about negative curvature Kähler-Einstein metrics. Okay.
So I have a question.
Yes.
So if you assume that more regularity, for instance, so if kx is bigger than f, so is there still a lot of difficulty in step one?
Yes. So actually, the proof we rely. So if you assume it's semi-ample, I guess it's probably. So it will be suddenly easier because you don't have any base point, but still, I think it won't be straightforward.
So you mean if there was no such assumption, it would be much more difficult than big enough cases?
So I'm saying they will still need, it will still require some real work.
Okay, I see.
Yeah.
Okay.
But probably from a technical point of view, it will be way lighter.
I see.
Yeah.
Okay, thank you.
Yeah, you're welcome.
Okay, thank you.
Okay, so yeah, as I was saying, this ends the parts about negative curvature, and again, as a summary, the theorem is called here. If you have a family of manifolds of general type, you can endow each fiber with the Kähler-Einstein singular Kähler-Einstein metric that yields a global current, at least on the smooth locus and the fibration, and that current is semi-positive and extends across the singular fibers. So let me now move on to the Ritchie-flat gates. Okay, and I'll try to see how much we can push the comparison with the negative case. So same setting, I start from a submersion. So this time I only allow smooth fibers. Submersion with compact fibers between Kähler manifolds. Okay, so I fix the dimension, it's n, and I fix a relative Kähler form, which will be my polarization. The relative Ritchie-flat metric, as you imagine, so I assume that each fiber is has a 0 first trend class. And then there is a way for me to glue all of the Ritchie-flat metrics omega y of x sub y in a sort of canonical, if not canonical, natural way. And that's the way that I explain in this box. I want to, so each of the Ritchie-flat metrics, I chose them to belong to the restriction of theta, a cohomology class of the restriction of theta. And so the relative Ritchie-flat metric can be written as theta plus the dt bar of somebody, I call phi. And phi is uniquely determined by two conditions. The first condition, is that its restriction to x sub y gives me, when I take the dt bar of that and add theta sub y, it gives me the Ritchie-flat metric of x sub y belonging to the cohomology class of theta sub y. And so that determines phi up to a constant, and that constant I can fix it by choosing that the integral of phi against my relative background Kähler form theta is 0. The reason I choose this normalization versus supremum normalization or something else is that this normalization is linear, and in particular, it varies well in families. It's a linear condition, okay? And so this tells me that this phi here that is clearly smooth in the fiber directions is actually automatically smooth in the base directions as well. Somehow it's a consequence of the implicit functions here. Yeah. Okay, so I've got this 1-1 form that's globally defined on the total space of my fibration X that restricts to the Ritchie-flat metric in my fixed cosmology class. And that's more natural than others, maybe. The conjecture, okay, in light of what I've explained above, maybe, is that this object, this global object, should pick up some semi-positivity just by the fact that it's Ritchie-flat in restriction to the fibers. Okay, and maybe you could conjecture too that the strict positivity would mirror strict variation in, of the complex structure. Anyway, so that was a conjecture. I'm not sure I have located it explicitly somewhere, but I've heard about it like forever. So I would not be able to locate like a place where like somebody said, okay, I suppose that this guy should be semi-positive. Long story short, the conjecture doesn't hold. Okay, and there are counterexamples, and that's what I want to explain in the second part. So, unlike the case of negative curvature, which picks up semi-positivity for free, this one in the Ritchie-flat case does not. Okay, so that's the second theorem joined with Junyan and Mihai that I want to explain today. And it is, okay, so it has a very geometric flavor. So the way it works is the following. Actually, as soon as mentioned two, there will be counterexamples. So we start from a K3 surface. The K3 surface can be made very explicit. It's some hypersurface in P2 cross P1 with well chosen degrees and so on and so forth. So this is very explicit and actually yields a family of examples. But anyway, so there is a K3 surface that satisfies the three properties below that I wrote below. Okay, so the first one is that it admits maybe before even the first one, it admits two elliptic fibrations P and Q on 2 pi 1 on 2 P1. And those elliptic fibrations are in a way transverse to each other. So more precisely, so the first fibration, which will be the one I'm looking at, P, okay, that will play the role of my vibration from the slide above, before. So P is not isotrivial, meaning that two general fibers of P are not isomorphic. The second property, as I was saying, is that the fibration P and Q are somehow transverse, the fibers of those. And one way to phrase that is that when I pull back O of 1 by Q, I get a long bundle on X that's P ample, so relatively ample with respect to that main fibration P. And the third condition, looks technical, but this will be crucial. You'll understand why in a minute, is that all fibers of P, so P will have singular elliptic curves as fibers. That's fine, we can't avoid that, since we assume P is not isotrivial. But I don't want them to be too bad, and too bad meaning I don't want them to be reducible, to have several irreducible components. I want all the fibers of P to be irreducible. So it turns out this is a very strong constraint on a K3 surface, on an elliptic fibration of a K3 surface. Okay, so what do we do from here? So, okay, I said we have that K3 surface and it's fibered by elliptic curves. And so I can pick a flat or Ricci-flat, it's the same thing, metric in each of the fibers of P, at least the smooth fibers, and that vary I choose them so that their cohomology class comes from a global bundle on X, and the bundle that I choose on X, so the role that was played by theta earlier, will be that bundle L. So you might object, and that would be a fair objection. Okay, if I go back to this slide here, L in my case is the pullback of O of 1 by Q, so it's certainly not ample, it's certainly not a positive bundle. Okay, so you might object that I'm constructing a counterexample that doesn't really satisfy the assumptions of my relative Ricci-flat metric construction, in the sense that it doesn't live in a globally killer class. It turns out that I'm going to prove that that relative Ricci-flat metric is not semi-positive, and it's smooth. And so this will imply, because that relative Ricci-flat metric is the limit of relative Ricci-flat metrics in C1 of L plus some ambient ample, that whenever the ample is small enough, the relative Ricci-flat metric in L plus this very small ample has to be negative somewhere, otherwise the limit when the ample and bundle tends to 0 would still be semi-positive. Okay, so all I'm saying is it's not a big deal that L in this case here, so we call you L, it's just Q star of O of 1. It's relatively ample, but it's not ample. Okay, and this is, it turns out that this is the key point. This is where we can develop some other, we can go through with the construction and derive the contradiction, is precisely because L is not globally ample, but only relatively ample. Okay, so first step. First step is the following. So I have this relative Ricci-flat metric, but it's only defined on the smooth locus of the fibration, right? I have no idea what phi should be, right? At local potential phi, what it should be when I'm on a single fiber. And so the first step is to say, well, assuming that omega, which is only defined on the smooth locus x naught, is semi-positive, 1x naught, then by general properties, because of the normalization that I chose, phi will automatically extend. So phi will automatically be bounded above near the singular fibers. And so that means that I can extend omega canonically across the singular fibers. And this is where I use, in a very important way, that all fibers are reducible. Okay, so that is explained in our appendix, in the appendix of our paper by Valentino Tossati, along with the choice of the K3 surface that satisfies the properties that I mentioned before. Okay, so what did we win? How do we improve the situation by extending omega? Well, now we have a global positive current in the cohomology class that's nef, but not ample, not big. So its square is 0, right? Its numerical dimension is 1. And because of that, so I have a semi-positive current, globally semi-positive on X, that's smooth on a big Zariski-open set. I mean big, a Zariski-open set that's not empty. And so by Buxom's criterion, if omega were to be strictly positive somewhere at just one point in X naught, if that were true, then by the singular homomorphic Morse inequalities, I would be able to construct a lot of sections for L, and way too many that are allowed since L is not big. So long story short, omega so I assume from the very start by contradiction that it's semi-positive. Well, it can't be strictly positive anywhere on x naught. And another way to phrase that is that the square of omega is identically 0. Or another way to phrase it is that at any point of x naught, there exists a direction along which omega vanishes. And now you probably see me coming. Let me move back up here. Omega is a relative Kähler because it restricts to the Ricci-flat, the flat metric on the elliptic surface, on the elliptic curves. Okay, so it's strictly positive in the directions of the fibers. And I'm telling you at each point of x naught, there is one direction along which omega is 0. Okay, so that direction has to be transverse to the fibers. But I already have a candidate for somebody who is transverse to the fibers. It's the foliation that's defined by Q. Okay, so let me come back to that now. Okay, the kernel of omega, which is a one-dimensional complex foliation, has to coincide, and again, there's a little computation to be done here, but it's really not difficult. Essentially, omega is actually the pullback of a metric on P1 by the map Q. Okay, so it tells you that the kernel of omega has to coincide with the foliation induced by Q, at least on the opens where it makes sense. And in particular, the kernel of omega, the Monge-Ampère foliation, which is a complex foliation but has no reason to be holomorphic, is in this case holomorphic. Okay, we get homomorphicity of the Monge-Ampère foliation induced by omega. Great. Now let me come back to my earlier friend. Okay, let's use horizontal lift of d by dt. So I worked locally on P1, and the P1 I consider is the P1, the base of the fibration P. Okay, so the one that really goes down in my drawing, my diagram. That lift, it's a smooth vector field defined at least on the smooth locus of my fibration P, and it lifts d by dt. Okay, so it's transverse to the fibers. And again, a very simple computation shows you that not only it's transverse to the fibers, but it's actually it actually cancels, it annihilates omega in the sense that it belongs to the kernel of omega. And because it's never 0, it actually directs at every point where it's defined the kernel of omega. Okay, so we have that foliation, kernel of omega, which is holomorphic, and we have that smooth vector field that leaves d by dt. That's maybe not holomorphic, but that directs this holomorphic foliation. And the key part is because d by dt, because v lifts d by dt, again, you can write down explicit coordinates and like play around with it, and that tells you that if v lifts d by dt, and if v directs one-dimensional foliation, that's holomorphic, then v has to be holomorphic. Okay, essentially, the fact that v lifts d by dt means that in the transverse direction, v is holomorphic. Okay, and we don't care about the other direction. Okay, so at this point, what did we get? We assumed that omega was semi-positive on x naught. We extended it to the whole x, and that enabled us to deduce that the kernel of omega was everywhere one-dimensional on x naught. And that was holomorphic, and we found a vector field that lifts d by dt that directs this foliation somehow, and that is holomorphic. But the flow of v, by definition, it moves one fiber of P to the other, right? Because it lifts d by dt. And because it's holomorphic, the local flows of v will identify general fibers of P. And that tells me that P has to be isotrivial. Okay, but I assume from the very start that I chose my K3 surface and those and that fibration that vibration P, precisely I chose it to not be isotrivial, okay? So the assumption that I made that omega was semi-positive can't be true, okay? And so that proves the theorem that, or that actually gives an example that can be localized if you want, that tells you that if you glue Ritchie-flat metrics, even flat metrics on elliptic curves, and what seems to be the most canonical way, well, they have no reason to pick up semi-positivity in the base direction. Okay, so what happens in the negative curvature case does not extend to the Ritchie-flat case. Okay, I think that was it. So French, thank you to all of you, and thank you for your attention.
Thank you. Thank you very much for the talk. And now it's time for questions and remarks.
So I have a question.
Yeah.
So can you choose the last beamer?
Yeah.
Yes. So so for the third step, why it's true? I mean, why is the kernel of this define the complex foliation, which is just the fibration of Q?
So the reason is that it's not an abstract reason. The reason is we know actually what the foliation is, because we know omega is the pullback. So let me. Omega lives in P star of Q of 1, and it's semi-positive. So it means that omega is the pullback of a form on P1 by Q.
Ah, okay. So you mean if you take omega is the form of the pullback, then it's automatically Ritchie-flat?
No, I'm saying that at this point I don't really use the Ritchie flatness. I'm saying that omega here, any current in the cohomology class of Q star of 1 is the pullback.
Ah, okay. I see.
Yeah.
But I don't know what's the difference here between for the Ritchie-flat cases and positive and the bigger cases. Why for this is a counterexample, but for the big cases cannot be. I mean, yeah, in big cases it's true. But I mean,
so the reason, if you're looking for a reason, I don't know, you see that in PDE. At PDE, you can write the same equation. You can write the same one in the case of zero curvature, and the factor identity disappears, and there's another factor that shows up. So you lose some ellipticity, not ellipticity, but you lose positivity property of the resolvent of the operator.
Ah, okay.
I don't know if that answers your question. Maybe I cut you off too quickly.
I see. Okay.
Yeah.
Okay, I see. Thank you.
Yeah. Henri.
Yeah.
So I have another question. Yes, that you mentioned that in your work with the Vincent and Ha. So you have proved that so for the omega it's of minimal singularity on x0. So how about so we know that it can be so we know that it can be extended canonically on x. So for this extension, so can we also say some about its minimal singularity?
It's a very good question. Truth be told, I only thought of that question yesterday when writing the slides, so I haven't given it more thought than this. I don't see a very simple reason why this should be true, but I'm not sure. I'm not sure what to think. So I don't want to speak too soon. I guess I should just say that I don't know. I don't know, but at this point, I'm not sure that there's a rationale for it. I'm not sure that, yeah. I don't know.
Because if x because if x is compactor, say in this case say in this case, if there is some single fibers which is non-reduced, so we know that for its C1 class of relative Canonical bundle, it should be larger than the multiplicity of the non-reduced fiber -1. So I don't know if in this case we can also say something by using Einstein matrix.
So can you say that just the last part again? I'm not sure I understand what you.
Yeah. So we know that. So for the first section class of the relative Canonical bundle, it's larger. Okay. So for example, for example, if we assume that for the basis of dimension 1, and we assume that so there is some non-reduced fibers over one point, and its multiplicity is it's the sum of AI times EI. So for some reduced dividers EI. So in this case, we know that it's C1 class. It's larger than AI -1.
Okay.
EI, the sum of this one. So maybe by using Einstein matrix, we can also know some.
So somehow you'd want to see that the relative K metric picks up little numbers on the non-reduced fibers.
Yes, probably. Maybe we can also show this, and maybe we can know more about its. Maybe we can know more about its regularity.
So quite possibly. Again, I don't have an answer for you right now, but I think it's a very interesting question, and I'll try to think about it maybe after the talk.
So for this theorem, can you say something on the bigness of the relative canonical bundle of C1Kx over Y? So this theorem, which
you mean if the family varies effectively?
Yeah, it varies effectively in some sense. Can you see directly so when there's some information on the effective?
So that's the $1,000 question. At this point, the short answer is no, I can't say that. It's a question that we've given a lot of thought to with Junyan and Mihai. And the analysis behind it is very tricky. At this point, we are not able to relate the Kähler-Einstein map to somehow some positivity of the relative Kähler-Einstein metric. It seems a little bit out of reach for the moment, but we'll keep trying.
But the 1 point is enough, is right? You just show omega is the 1 point.
Of course, 1 point is enough, but in all these problems, and it doesn't look completely obvious on the construction. All these problems are very much global, and having one singularity in 1 point affects what happens very far away from that point. And this is a bit annoying that unlike the one fiber case, unlike the absolute case of one Kähler-Einstein metric on one manifold, where we can completely separate the analysis from what happens on the Ampelocus and what happens away from it, where we can actually localize the problem. So that's in the case of the absolute case. In the case of families, this is not possible anymore.
Okay, but actually,
yeah.
But if the family is effective, then we know that the Kx of Y is big, right?
So we know, yeah. I guess I understood your question as, can we recover that using K metrics? Yeah.
Okay, thank you.
Yeah.
Some other questions or remarks? Okay, if there are no more, then let's thank the speaker again, and thank you very much. Okay.
Thank you. Thanks.